Welcome to EDU World Space.
Okay, so we're given a hollow aluminum cylinder of length 2.5 meters, inner radius of 2.75 centimeters or 2.75 times 10 to the minus 2 meters, and outer radius of 4.6 centimeters or 4.6 times 10 to the minus 2 meters. And we're told to treat each of the surfaces as an equipotential surface. And in part A, you're asked to find the resistance between the two faces of the cylinder. So the faces are this area right here, the circle. And we're also told that an ohmmeter is connected between the two faces. So you have to find the resistance. And to do this, you can use equation 2510. So let's write down equation 2510, which tells us that the resistance is the resistivity times the length over the cross-sectional area. We're already given the length. We're told it's aluminum, so we can find the resistivity. But we don't know the cross-sectional area. However, we can easily find the cross-sectional area by keeping in mind that the the part where there is no aluminum is in the inner radius. So aluminum exists between the outer radius and the inner radius. So kind of in this shaded region here, this is where the aluminum is. So let's say RD, which is the difference between the outer and inner radius, that is the radius in which the aluminum lives. So then we know the area is pi r d squared, which is pi times r o minus ri squared. And we're given the outer and inner radii in the problem already. So then we can find the resistance. It's the resistivity of aluminum, which is 2.75 times 10 to the minus 8 ohm meter, times the length of the cylinder, which is 2.5 meters, divided by the cross-sectional area, which is pi times 4.6 times 10 to the minus 3 minus 2.75, that's meter, times 10 to the minus 3 meters squared. And when you plug in these numbers, you find that the resistance is 6.39 times 10 to the minus 3 ohms. So that's it for part A. Now we move on to part B. And in part B, your ohmmeter is connected between the inner and outer shells. So it's the inner and outer surfaces. So let me draw a picture to sort of make that clear. So here's our cylinder. And the ohmmeter is connected to the outer part and the inner part. So here. And what happens when it's connected like this is that it causes the current to flow radially, right? The current is going to flow between those two surfaces. So in this particular case, we have a radial current. So this is part B, as opposed to part A, where we have a current that was flowing along the length of the cylinder. Now, in order to actually calculate the resistance, we use a form of equation 2510, but we need to use a little bit of calculus. So it's the same idea, except that your cross-sectional area now is different. So let me what we'll do is establish a thin cylindrical shell. We're not really doing it justice by drawing a proper circle, but let's say that this circle here now is itself a thin cylindrical shell, which has a radius r and a thickness. That's this sort of red region here that I'm poorly attempting to shade in. Let's call that dr. Okay, and so now the resistance, or rather the differential, the small portion of the resistance, is the resistivity. This is not changing. We're assuming that this is constant, times the sort of the dr, which here in part A, this was L. This was the length, over the cross-sectional area. But in this case, the cross-sectional area is given by pi r squared times, or rather 2 pi r times L. So the cross-sectional area is the flow of current through this cylinder here. So the area of this thing is the circumference, 2 pi r, times the length L. Right? And so then dr is equal to rho, the change in the radius, divided by 2 pi r L. And if we integrate both sides, then we have the resistance is equal to, let me just pull out all the constants, 2 pi L, the integral from the inner radius to the outer radius, dr over r, which is equal to rho over 2 pi L. And this, you can look up this integral. This is actually the log of r. And we have to evaluate this at the inner and outer radii. So let me do that on the other page. So we have r equal to rho over 2 pi L times the log of the outer radius minus the log of the inner radius. And when you have something like this, you could just use one of the log identities that when you subtract two logarithms, you have a division. So let me just write that in a neater way. Rho over 2 pi l, the log of the outer radius divided by the inner radius.